Good, this is our unit 5 and the first part of our airtightness presentation. So first we want to ask the question, why do we need airtightness? Then we want to talk about the planning task that it is. Now here we've prepared for you, before I start this airtightness thing, a few Passivhaus fundamentals. And this is something that you can hopefully always refer back to after the course. And this is your common sense corner. And we will sort of talk about these as we go along and fill in those little gaps. You already know some of them now, because the thermal envelope, we've just talked about the thermal envelope in our thermal insulation materials. And we know that the thermal envelope must be continuous and complete. So we don't want any gaps. We want a continuous and complete thermal envelope around our building without any gaps or any missing parts in it. Now, what we're going to talk about now is the airtightness system. And the airtightness system, so this is here now, or this one also we know, number 4, the ventilated cavity is not a part of the thermal envelope. We talked about that as well. Now we're coming to number 5 and number 6. That's what we're going to talk about now. The airtightness system is a part of the thermal envelope, and so it needs to be continuous and complete as well. So we will talk about that. And the airtightness system is a structural component, and we'll talk about that as well. So these are the ones that we can already fill in, and we will come back to that over the next few days. Good. Why do we need airtightness? So if it's cold, and if it's only cold, then your woolen jumper keeps you nice and warm in winter. But if it's cold and windy, so if you take that woolen jumper now out in the windy day, then that woolen jumper doesn't do much for you. It's still cold in that jumper. And why is that? That's because those little air pockets that we talked about are now disturbed. You know, those little air pockets aren't protected. The wind is going through them. And now those still air pockets aren't still. They're moving, and that external air is getting to you and you're cold. So it needs a windbreaker jacket over the top of your woolen jumper to keep you warm. So that's exactly the same thing what we're doing with our thermal insulation. So the thermal insulation doesn't perform if the air is moving through it, because air movement always means heat transport. But only once you stop that air movement, then we can talk about the thermal insulation. So thermal insulation means still air pockets where the air can't move. And only if the air pockets are protected against air movements, then we have an insulating property. And that's exactly what we want to do. We want to do with our airtightness. We want to protect our thermal insulation from air movement, and we want to isolate the indoor environment from the outdoor environment from air movement. Good. So what are the impacts of air leakage? So why is it so bad to have air leaking out of your building or into your building? Airtightness can solve a lot of problems. So we can have health issues like mold, smoke, and other particles. So obviously, if you have a leaking building, anything that's outside can come to the inside. We could also have a problem where we can have mold risks, because there's moisture happening, moisture transport, and we could create mold issues. Then comfort issues like draft, cold surfaces, noise, and odors. Most of us know that now that it's winter. Drafty homes, if there's a storm happening, Perth had quite a few windy days. That wind was going all through my house. Cold surfaces, noise. So yeah, obviously if there's air moving through, all that airborne noise is going through as well. Energy efficiency issues. So if we're losing air through our gaps, that air transports energy, and that energy is lost. So through our gaps and cracks, we're losing a lot of energy, or we're gaining a lot of energy in summer. And then we could have structural issues like dry rot. So air movement also means that there's moisture moved, and we could have problems in our structure. It could be a fire hazard as well. So you can see with air tightness, we can solve all of these problems if we're doing that properly. There's a little bit of a graph there as well. So have a little bit of a look at that. It's very interesting here. So what are the airtightness system requirements? So our airtightness system needs to be continuous. That's what we said before, continuous and complete. It needs to have strength, so structural integrity. Why is that? Because we're testing our airtightness system, and we'll talk about that this afternoon, with 50 Pascal. So we are putting pressure on that airtightness system when we're testing it, and it needs to withstand that. If that falls apart, then it wasn't strong enough. And in reality, it's what, if a storm's coming in, you want that system to withstand that storm as well. Okay, so it's unlikely that it goes up to 50 Pascal, but this is what we're testing it for, and that's what it needs to be strong enough for. It needs to be durable, and it needs to be airtight, so air infiltration, impermeability. Obviously, that's what we want to reach. Good. And here's an example where they've used a membrane for it, but we don't have to use membrane. We can use other materials as well for airtightness, which I will introduce to you in a second. So there's two types of leaks, two types of air leaks in our buildings. So we can have one that's called an energy leak, and they're an issue of energy efficiency. So it's a big quantity of air that's leaking uninterrupted. And the thing is, there's usually so much air moving, and the air is moving so fast that there's not enough time for condensation. So this could be your gap under your front door, where your postman can deliver your parcel under without you opening the door. That is usually your energy leak, and you usually don't have moisture underneath there. That's because the air is flowing too fast, but you're losing a lot of energy through there. And the second one are moisture leaks, and they are an issue of condensation. So now you have less air leaking at a slower pace. So in this case, it's a small leak. The air has a lot of time to cool down. And when air cools down, it reaches its dew point. And that means moisture can now form. In this case, it forms here right behind that external surface and forms nice moisture here. And this is where you will see your mold, your rot, and everything in that structure. Okay. So the quantity of air leaking. So if we're doing an airtightness test, doesn't really tell us what type of leak we have. So if we have an airtightness test and it tells us 5 air exchanges per hour, it could be because we had a window open, or it could be because we have a lot of little leaks. Okay, so it doesn't tell us that. However, if we have the 0.6 air exchanges per hour, the chances of energy leaks are small. So it's mostly then your little leaks. And you can see that still there is a little bit of a risk of moisture. And we need to manage that. And we will talk about how we can manage that little bit of moisture that's still going through our build-ups and how we best get rid of that. Good, so that's our smaller quantity, that's our moisture leaks. Now I want to show you how big the problem can be with airtightness, or with if you don't have proper airtightness. So let's see, we have here an airtight construction. And what happens in an airtight construction, we still have diffusion. Okay, so the diffusion means that vapor moves through a material, and that diffusion gives us 0.5 grams of water in that structure per square meter per day. Okay, remember that number? Oh, it'll stay there anyway. But what would happen if in this 1 square meter of structure we have now a 1 millimeter gap? That Fuge is a German word for gap. So 1 millimeter gap over that 1 meter. Maybe have a little think about what you think, how much water we would have if we'd have that compared to our vapor movement. So that 1 millimeter gap gives us 800 grams per square meter a day. Imagine 800 grams, that's almost a liter of water that you pour into your structure every day, and that your structure has to handle because of that 1 millimeter gap that is not made airtight. Now you see how important it is to get your structure airtight. Okay, because there's a lot of moisture that can go through your structure, and that can cause a lot of problems. The other problem is now that your thermal insulation is compromised, because we have air movement through it, we have moisture in it, the heat transfer is 4.8 times higher. So in this case, we would have to make this 700 millimeters thicker to make up for that heat loss. Okay, so you see the performance goes down, the risk for mold goes up, the risk for structural damage goes up. So airtightness really is key here. Now, where do we position our airtightness system? What do we do? How do we do this? So we have here cold and hot. Okay, it doesn't matter whether it's outside or inside, just cold and hot. That's what we always have. We have one side, or sometimes of the year it's the same inside and outside, but often it's one side is hotter than the other. And the risk always comes from the hot side, because now we have to go back a little bit into physics. So hot air can hold more moisture. Okay, and once the hot air cools down, and it can hold less moisture, we come to a so-called dew point, and then we have condensation. So this is what happens when you take your cold beer can out of your fridge. That surface is colder, the hot air goes onto that surface, cools down, comes to a dew point, and that's where condensation happens. So the risk always comes from the hot side, and we want to stop that air from the hot side to the cold side. Okay, so our airtightness system always on the hot side, on the warm side of our structure. Whether that's inside or outside, we have to see now what our climate is. In most of the climates where we all live in, unless one of you lives in Darwin or something, we would still consider our inside our warm side, because for a lot of times of the year, the inside is warmer than the outside. Yes, we have the other way around, but yeah, we will talk about that as well. What happens then if we have the reverse situation, but we would still prefer to do that on the inside and consider that our warm side of our thermal envelope. Good, so that's where we want the airtightness system. Now let's talk a little bit about those that airtightness levels. So our airtightness level of 0.6 air exchanges per hour, we remember now that this is our Passivhaus certification value that we need to reach if we want to have Passivhaus certification, and that the remaining moisture from air leaks, that we can handle that. So, you know, we still have, we're not building for space. We're not building with 0 air exchanges. We're still allowing 0.6. And we've learned now that, yes, there will be some air leakage and some moisture in our buildup, but it's so little that we can handle that by saying, okay, let the moisture diffuse to the outside, and there it will be taken away. So it can dry out. The structure can dry out. That's what we want. If we have 1.5 air exchanges per hour, if we have a heat recovery ventilation system, then we can say it's mostly safe in mild climates, and we don't have too much pressure losses with our HRV system. So 1.5 is still okay. If we have smaller than 3, that's a must. Still a risk about 20% for moisture leaks. But if the holes are known, maybe we can say, okay, it's an energy leak. Maybe we have somewhere a bigger gap, and that's why it's 3 air exchanges. But we have to be a little bit more careful. Now, the really risky part is between 3 and 10 air exchanges, because now we have an unacceptable high risk. We have high moisture leak risk. And this is where we can really now create the problem. So if we have really leaky buildings, so leaky buildings where we're saying we are above 10, then it's mostly energy leaks. Okay, so all our conventional buildings don't have mold because we have so many leaks that the air is usually exchanged. There's a lot of energy leaking out, but we have not so much moisture risk. But because if we're making it now more airtight and create smaller gaps, we still have high moisture risks. And if there's too much moisture in our buildup and it can't dry out, then we're creating that risk of mold or rot or structural damage. So this is why Passivhaus is going down to 0.6. The risks are very low, and they're saying 0.6 is achievable with, you know, with not too much effort. So 0.6, if you're experienced, is a good way, is a good number to achieve for your airtightness. Good. So again, positioning of our airtightness system, we've heard now on the warm side. So from the warm side, we want to stop it. In a cold climate, that means that on the inside, we want to have our airtightness layer. We also want to have our vapor tightness or vapor control. that is often one system. So one system can provide both of these things. And then on the outside, we have our weather tightness, like we always have, because the weather is always on the outside. Then in a hot climate, we don't need nothing on the inside, but on the outside, we now need our air tightness, our vapor tightness, and our weather tightness. Also, that can be one system. And we're talking about hot climates. I would say like Darwin is a definite hot climate. Brisbane is probably already could be considered a hot climate, where we mostly have our, sort of our warm side from the outside and our risk coming from the outside towards the inside. If we are in an area where we're not quite sure, then we need to test our buildup, and it can be tested with a program that's called WUFI. So it's a program that models the moisture buildup in your buildup over a few years of time, and it tells you if there's a risk of moisture building up or if the structure is drying out, and then you know if your structure is at risk and where to put your air tightness layers. But generally speaking, air tightness and vapor control should be on the warm side of the thermal insulation. Okay, so the warm side of the thermal insulation. For cold climate, it's very clear, it's the inside. And for mild climate, preferably want to put it on the inside as well, for various reasons that I'm going to be talking about. But this is the general rule of thumb. So priorities for moisture management is, this is an interesting one, because we have through a wall, we have diffusion, we have air leakage, and we have liquid water. So now you can see if diffusion has the priority of 1, then air leakage has the priority of 100 and liquid water of 1000. What does that mean? What I want to say with that is that if we're not having our building under control in terms of liquid water, if it rains through the roof, then we don't have to worry about air leakage and our air tightness. Okay, so first you want to make your building waterproof. You want to make sure that that's all fine. Then you want to make it airtight. And once you've got that under control, then you can look at your diffusion. If you don't have the air tightness under control, you don't have to worry about your vapor movement through your structure, because that's so minimal compared to your air leakage that it doesn't matter. So this is our priorities. Liquid water first, air leakage second, diffusion third. Ideally, you want to have that all under control. But if we don't have one of them under control, then we don't have to worry about the others. So if you don't have your air tightness under control, you don't have to worry about your vapor. Good. So that's, I think that's important to know, because it makes sense in your, in prioritizing or where to put most of your energy in. Good. Then air tightness is a planning task. So plan the air tightness system carefully, avoid penetrating the air tightness system. And obviously we need to penetrate it at some point, but plan all those penetrations for services and so on. Plan them carefully and plan all changes of direction or material. So if you want to now, let's say you're using a membrane in the ceiling, but you're using a render on the wall, put a detail somewhere. How is that membrane connected to the render? Let your builders know how they need to do it. Otherwise, it's not going to work. Okay, so plan all that. Make sure that you know how that should look. Don't leave it up to the people on site to figure it out. And then that's usually where it goes wrong. We call it the green pen test. So you want to be able to run a green pen around the whole perimeter of your building at every corner, knowing what is happening with your air tightness. Okay. Also be careful that it's not only on a one level, but if you're having a two-story building, that you also need to know, how do they overlap? How does my top story come onto my ground floor? So what happens in an area like this, where all of a sudden I have something that is inside, you know, it's like an inside area on the ground floor, but it's an external area on the top floor. How do I secure my air tightness? How do I finish my thermal envelope in this area? Okay, so there's tricky bits. Floor over unconditioned porch. How is it insulated and air sealed? Difficult air barrier to execute. So if you have little corners like that, then in this case, is this room conditioned? Where does the insulation and air barrier go? So really have that in mind when you're designing your buildings. And if, as you can already see, a more compact building would make this a lot more easy. Okay, so try and keep it compact, keep it easy. That makes your life and the life of the builders a lot easier. And it makes it a lot safer that you can actually execute your airtightness properly. Then we're coming to the Passivhaus airtightness requirement. We've looked at that a little bit already, and that's our 0.6 air exchanges per hour. So N50, that's our airtightness requirement, 50, because we're pressurizing it to 50 Pascal. So this is at a 50 Pascal pressure difference. 0.6 ACH stands for air exchanges per hour. It also, like the unit for this, there are different ways to express this. So ACH is 1, hour to the power of -1 is another one. Or you could write this one as 1 divided by hour, so per hour. And all of these three are okay, just so that you know that all of these three can be used as your unit. So the definition, N50 is the air exchange rate at a pressure difference of 50 Pascal. And it's calculated by the measured volumetric airflow rate at a pressure difference of 50 Pascal in relation to the building volume. So what you need is you need to calculate your building volume, and then you measure, and we'll learn how to measure that in our next unit. You measure the amount of air that's going through that envelope, and by having those numbers, you can then define our N50 value. So it's our V50, that's our measured airflow rate, and our VN50, that's our reference volume, so the volume of our building. And the net air building volume is measured from finish to finish, excluding internal walls, internal doorways, and separating floor levels. So it's really just the air volume that's in your building.